Sounds good.
Hello, everyone. Welcome to the Monday seminar. Welcome to 2024. Happy New Year to you. Yeah, I'm excited to restart our seminar series. This is a seminar series that's been going on for a while now. It started 4 years ago plus. I did some counting today. We've had something like this is a 115th seminar that we've done at this Monday time slot. Started in a different era where we were dying for interaction, and we are still excited about interaction. Maybe we're not dying for it anymore because of the renewed ability to travel. But we realized during that time that yeah, something interesting can happen like this. We can connect across the world and across disciplines in an interesting way that's not really possible in other formats. So happy to have the opportunity for this. Really thankful for people like Christelle, in particular, to be in here today, to go through what isn't the funnest. It's not, as you all know, not the best, most exciting way to give a talk into a screen by yourself. But there's an opportunity for different interaction, and I really want to encourage people to participate in the discussion, to plan on that, to plan on joining us. Typically, we have up to a half an hour at the end to have a discussion, an elongated question and answer period. Christelle, if it's okay with you, please tell us. Sometimes people interrupt with points of clarification along the way. Of course,
yes, please. Yeah, please feel free. And I might not see the chat or the raise hands, but so just unmute yourself and speak up. Maybe Chris, you can monitor in case there is raise hands or chat questions. Nice. Yeah, feel free to interrupt me anytime for questions or clarifications. Absolutely. Yeah.
Okay. Well, nice to see you all, and thank you very much, Christelle, and I'll turn things over to you.
All right. Yeah. Thank you, Chris. I want to say also that I'm very happy to have the opportunity to give this seminar to this audience. Chris actually helped me write my NSF career proposal a little bit that got funded. And most of the results that I'm going to present today are stemming from that opportunity. So yeah, thank you, Chris, for helping me out on this. And I'm excited to share some of the results with you and the other members of the community. So basically what we're going to talk about today is volcanic landslides. Okay, so I'm going to try to better characterize some of them using ground deformation data. And, as most of you know, the volcanic landslides and we're going to go through that, they have different behaviors. They can be slow, they can be transient, and they can evolve in catastrophic flank collapses, like the famous example of Mount St. Helens in 1980, that was the first catastrophic collapse event that was actually caught on camera. And so we have extensive photographs showing the evolution of, like, this is Mount St. Helens right before the collapse started. And then you can see that the loop of this landslide is seen here. And basically, like, most of half of the edifice is starting to slide, and it's super fast. Obviously, we're looking at a few seconds. And if you're dealing with an active volcano, if you are removing mass on top of a magmatic chamber or something, you are basically removing weight and allowing for a catastrophic depressurization of the magma reservoir that, on top of the landslide, can lead to a massive eruption, leading to a lot of ash and pyroclastic flows that can reach far distance from the volcanoes. So this is a pretty big hazard, and it's important to work on this topic. Let's see. Yeah, so and this is something that has killed people. So about 20,000 casualties, even more than that now, in the past 400 years, due to related to flank collapse at volcanoes. And if you are dealing with a volcano that is on the coast, like Etna, or which is also an island volcanoes like Hawaii, or Anak Krakatau volcano in Indonesia, on top of the landslide and eruption, you are dealing with a tsunami risk. You can have again, you're making this huge part of the volcano collapse, slide into the ocean. And so you can generate a very big tsunami. And that's what happened in 2018, for instance, at Anak Krakatau, where this volcano here was looking like this dashed line before. And in 2018, in December, you had a catastrophic landslide, catastrophic collapse. And this is the edifice post-collapse with the sliding interface landslide loop here. And you can see that you still have some debris in the water. That's why the water is kind of brown on this side of the volcano, because that picture was taken quite shortly after that collapse. And that collapse generated a tsunami, and that's what killed people there. Hundreds of people died because of the tsunami that was not anticipated properly. So, the manifestations and the mechanism behind the triggering of flank instability at volcanoes remain quite poorly known at this point. And in particular, one thing that I'm trying to tackle in my research is how you get from a volcano that has some sort of instability, so that's generally an active volcano, so you have magma pressurized in reservoirs, sometimes magma intrusions that can facilitate the collapse. Perhaps maybe you have a flank that is moving slowly, creeping, and then at some point you have a catastrophic flank collapse, this massive landslide associated with a big eruption and a potential tsunami. And basically I'm trying to see if we can find some insights and triggering mechanism on how we get from here to this unstable volcano that is not a threat to here, to that big, massive hazard. So how do we transition from some instability, maybe slow motion, to a catastrophic collapse is one of the big questions that I'm working on. All right, so this is the motivation, deadly, poorly understood. So we need to do better about that. And I'm gonna give you a little bit more background on the triggers and the types of instabilities that we are dealing with at volcanoes. After that, we're gonna go in 3 cool places. We're first gonna fly to Indonesia and look at some data and mechanisms that happen at Anak Krakatau volcano, the one that I just mentioned that had this massive collapse in 2018. And then we will take another flight and go to Guatemala, and we will look at a volcano called Pacaya volcano, which also has experienced in the past very big collapses and is unstable and very active. And finally, we will go to one of my favorite places in the world, Hawaii, and we will look at a volcano that is more monitored, more understood, but still not everything is clear at that volcano. And so we can tackle some interesting problems there as well. All right. So when you have a volcano, there are, many factors that can help prepare or trigger some sort of flank instability. And, you can imagine that when you have magmatism, so you have an active volcano, you have magma at depth. So these overpressurized magma reservoirs and magmatic intrusions, especially diking, can really stress the edifice and can create some asymmetry that can help flank instability. The loading itself, obviously, you are dealing with a very dynamic process over time. You're building your volcano over time with different layers, different mechanical properties, potential, different layers that can, maybe a layer can be weaker and can help becoming a fault interface. So these type of things obviously matter. Rainfalls can also play a role in helping lubricating faults, things like that. And if you have seismicity happening, which is often the case at an active volcano anyway, the earthquakes can also induce some stress change transfer that can help the volcano being unstable or transition into another phase of instability. So there are many factors, and I'm not gonna look at and model at all of these. They all are important, but what I will consider as the most important ones that I'm going to study here is the loading, so the weight of the edifice itself, magmatism, since I'm looking at active volcanoes. And also I will touch a little bit on the strengths of rocks and, heterogeneities being an important factor. So about magmatism, we have actually a few neat examples, recent examples of how magmatism can actually help trigger flank instability. So we have basically two nice examples. One is the left figure here. This is the situation that we have in Hawaii at Kilauea and Etna volcano in Italy as well. And we basically have diking, so magma intrusion, vertical magma intrusion happening below a summit and rift zone at a volcano. And we have this, overpressurized magma that is pushing part of the edifice to slide along a low angle fault, often called décollement or detachment if it's a normal fault. Another example is at Piton de Neige. So Piton de Neige and Piton de la Fournaise are on La Réunion Islands in France, in the Indian Ocean. And so we have interesting exposed features at Piton de Neige, which is the old volcano. Piton de la Fournaise is the very active one. And they're like, kind of buttressing each other. They're like very close to each other. And there are exposed, dike intrusions that basically show that some magma are intruding in pre-existing faults at Piton de Neige volcano. So that's another example of very strong interaction between the magmatism and the faulting processes. Another very neat example, the neighbor of Piton de la Fournaise, Piton de la Fournaise volcano, very, very active volcano. And a recent study looked at 57 dike intrusions from 22 years of satellite geodetic data, or INSAR, so ground deformation data measured by satellite imagery. And they modeled the deformation from these dike intrusions. And this figure here show you all these dike intrusions projected together. So this image here is a map view, so map from above. This is Piton de la Fournaise. This is the Enclos de Fouquet caldera, and all these, eruptive fissures in black. This is the east-west cross-section here, which is probably the most, neat thing about this figure is that you can really see all the dike intrusions kind of aligning along a consistent feature here, which is basically the fault plane under which the volcano is unstable and kind of slipping seaward. And this one is a north-south cross-sections. So basically that study was really interesting and revealed that it looks like dikes are facilitating and intruding along a deep-seated décollement feature at Piton de la Fournaise. Okay, so we know that happens at volcanoes. We talked about a few of them, but is that frequent? Is that something that happens a lot? Do we have a lot of volcanoes that are unstable, or is it a very limited number of them? Well, if you're like me and you're like sometimes just looking at Google Earth and like, going around the world and looking at zooming in on volcanoes and zooming out, you and any tectonic settings, subduction zones, ocean islands, whatever, if you do that, you can actually see that there are a lot of landslide scars present on volcanoes. So for instance, here we have this volcano Pacaya that we're going to talk about in Guatemala, which has a very asymmetric feature and a very clear 100 meters high scar that is the witness of a past collapse. And if you look at other volcanoes like Anakrakatoa, we already talked about this one. And then in Japan too, we have a bunch of islands that experience past collapse. And again, you can clearly see them just looking at the geomorphology of the volcano. And other volcanoes in the Aleutians and on subduction zone in Central and South America are experiencing as well. So yes, it is very frequent. It is a pretty ubiquitous process that happens at volcanoes, that at some point during their life, they experience some instability of the edifice. All right, and so we talked about, obviously, the catastrophic collapse, massive landslide, because that's one of the biggest threat, natural, hazard threat related to active volcanoes. But that's not the only thing that can happen. There are other types of flank instability, flank motion that can happen that I kind of listed here. So beside the catastrophic collapse, we can have transient slip. So we can have part of the edifice slipping along a fault and not necessarily leading to a full collapse event. So kind of similar to a landslide, a quite fast fault motion. And then we also have slow slip events, similar to what we've been observing at subduction zones for a while now, that have been recognized only at a couple of volcanoes, including Kilauea volcano and Etna volcanoes. Basically, very densely monitored volcanoes. So you have slow slip events and little, tips in the GPS stations on an unstable flank that kind of show you that they are happening. And then you have other volcanoes that are experiencing a longer term type of instability that I'm very interested in, which is what I call a persistent flank instability, where you have a longer term, multi-years, okay? I'm talking decade, maybe multi-years, slow motion, that it's not very obvious unless you are really looking closely at the formation data, that it is happening. And so that's one that we're going to talk about a lot, because I think it's very important to understand how you would get from this slow motion into something faster and potentially more destructive. So persistent flank instability, there was a study here by Poland et al. That attempted to come up with some framework for that process to happen. So I'm going to walk through to this figure here. The x-axis is magmatism, so not very active volcano on the left, very active volcano on the right, meaning low magma supply on the left, potentially smaller edifices, higher magma supply, and larger edifices to the right here of that x-axis. Y-axis, you can think of it as the structural setting. So we have young interplate with potentially thin, weak substrate at the bottom of the axis. And if we go up, we have older plates and thicker substratum, for instance. And so they basically plotted volcanoes that are known to experience flank instability, like Piton de la Fournaise is here, Etna volcano is here, and Hawaii volcanoes, Mauna Loa and Kilauea volcanoes are here. And so basically, if you go that way along this arrow, you increase the rate of flank motion. So you have faster slip, persistent slip. And then we have a couple of volcanoes, like from the Canary Islands. We are not sure if we have slow slip, long-term happening. And like the Galapagos volcanoes, apparently we don't have this process happening. And so there was an effort to kind of try to delimitate the field in which the conditions in which you would have persistent long-term flank motion happening, basically. So when you look at this, of course, you will think, okay, we have some sort of knowledge gap here, because we have only long-term flank instability recognized at a few volcanoes, Hawaii, Etna, and Piton de la Fournaise. So why is that? Is that due to a lack of ground-based instrumentation? Again, Etna, Hawaii, and Piton de la Fournaise are one of the most instrumented volcanoes on Earth. So is that due to that? Is that because slow persistent flank instability happens below detection threshold? Or is it obscured by other signals? So this is an interesting point to investigate. And then there is a lot of debate on the mechanism, both triggering and sustaining flank motion. So basically, the taller, larger the edifice is, like Mauna Loa volcano, massive, tallest volcano on Earth, gravity-driven slip, loading should matter a lot. But we've also seen that collapses are more frequent on active volcanoes. So it looks like shorter timescale transient processes related to fluids and magma matter a lot as well. And so, keeping these questions and this big picture in mind, we're going to be looking at these three examples that I mentioned before. So first, Anak Krakatau, Indonesia. All right. So just for the story, Anak Krakatau means the child of Krakatau, also spelled Krakatoa. And there was a massive eruption that you might have heard about in 1883. Krakatau was actually here. That was this entire edifice here. And it had a massive eruption as powerful as the recent Honga Tonga 2022 eruption. So we're dealing with like a very big intensity, VEI, volcanic explosivity index, very high eruption of 6, a lot of ash, and also trigger a tsunami in 1883. It was estimated that, over 36,000 people died due to that eruption and tsunami. So that volcanic edifice got blasted off. And you have 3 remnants here, the 3 green islands that are the remnants of that, Krakatau edifice. And after a little while, a new baby volcano popped up from the ocean, Anak Krakatau, which is this guy here, which is more or less located at the center of that previous caldera system. And it is very active and is unstable. So again, in 2018, this volcano, picture here, collapsed suddenly and induced over 400 fatalities due to the tsunami mostly. So it's like a map view here of the edifice, and after the collapse, again, you have like a big chunk of the edifice that slipped about over 200 meters high, that slipped in the ocean. And so we know it's an active volcano, and the tsunami was actually something that people thought about in a study by Giacchetti et al. In 2012, in which they modeled the plausible flank collapse that could happen and kind of basically forecasted the effect of the tsunami that happened in 2018. But for the 2018 thing, I mean, there was no ground-based sensor on the volcano. So it was also a very cloudy period. So even images from remote sensing could not really tell what happened. The tsunami took everyone, by surprise. And it's only by looking at radar images, and then when the cloud dissipated and you can actually see what happened, that actually you realize that more than half of the edifice collapsed. So coming back to our research questions, we wondered, is that volcano also experiencing longer-term persistent flank motion or not? And also, can we try to identify any potential precursors to that 2018 collapse? So what we're going to do to tackle these questions, again, I told you there is no ground-based data available before 2018. However, we have hundreds of radar satellite images. And so we can use this method called INSAR, Interferometric Synthetic Aperture Radar, to come up with ground deformation maps. And we have data since 2006. So the x-axis here would be time. So it starts in 2006 and up to present, basically. And my PhD student, Young Cheol Kim, is working on that massive data sets, processing hundreds and hundreds of images from different satellites. ALOS-1 is one satellite. Cosmos SkyMed is the Italian constellation, very powerful to look at these type of processes because we have very frequent acquisitions. And the more recent Sentinel-1 European Space Agency satellite. And so we're looking at hundreds of images, processing them into ground deformation maps using INSAR time series analysis. And we have ascending orbits when the satellite is orbiting from roughly the South Pole to the North Pole. And we have data along descending orbit when it's orbiting roughly from the North Pole to the South Pole. So we have different line of sight, different looking angles, which helps us identify better the mechanism when we do some modeling. So when you look at these ground deformation maps for different time periods, something obvious is popping up. You have a deformation pattern in cold colors, basically, that is visible on every ground deformation map that we process. So this is the island of Anakrakatau, and this is basically the landslide scar, okay? So that's this edifice is, this part of the edifice is what slipped in the ocean in 2018. And you can see that basically since 2006, there is actually deformation happening there. And it's blue colors, meaning that the ground is moving away from the satellite. So line of sight, the ground is moving away. So it's like a slow landslide basically happening. And again, since at least 2006, maybe even before that. So when we look at the same data set, when we plot at an area deforming over time for the same data set, so this is an area on the unstable flank over time, so from 2006 here until 2011, and you see we're dealing with like, about 4.5 centimeters per year. So this is a significant motion. Cosmos SkyMet, which provides this very nice sampling because we have many, many images. In here, for instance, it's 2012 up to 2015. And you see you have something very steady that is happening, about 15 centimeters per year of motion. So again, we're dealing with something quite significant. And then we have a few interesting steps that are happening, that are changing a little bit the rate that we think are important as well. So basically, looking at in-star time series, we are showing that this volcano has been moving. The unstable flank has been moving for over a decade before the December 2018 collapse. So to answer the first question, is Anakrakatau also experiencing persistent flank motion? I hope I convinced you that yes, it is experiencing long-term flank motion. And it's just a matter of processing enough data carefully to actually see that in the data. And then the second thing that we are trying to look at now, were there precursors to the collapse and what is the exact trigger? Some geochemistry analysis of the lava and the products emitted in 2018 suggests that there is no evidence for the collapse being triggered by magma supply, magma ascent. But we do see interesting inflection points, interesting steps in the deformation rate, and also potentially slight change in the deformation pattern on the ground deformation maps. And we think they are correlated with magmatism and volcanic activity. So right now we're looking into that, and we're trying to understand if the flank rate of deformation is basically modulated or affected by magma supply at that volcano. All right, so that was the first example. Second example, at Pacaya volcano in Guatemala. Different areas, still subduction zone setting. We are looking at this map view. We have this collapse scar here that is very visible on this photograph here as well. We have a bunch of lava flows that happen outside of this collapse scar, but most of the activity is located at the summit. You have a lot of ash, a lot of lava flow happening in that new cone, the McKinney cone, which is located inside the landslide scar. So very active, many lava flows, especially at the summit. Slopes are quite steep as well. And there is evidence for this past catastrophic collapse along that scar that happened. It was a massive debris avalanche that happened, along this basically southwestern flank slipping about 1,000 years ago. map view of the volcano. And then here you have a cross section, XX prime, that is shown here, which is our basic understanding of, we have this modern Makani cone here that builds up on a weak layer that is this ignimbrite layers that is the result of that massive debris avalanche from 1,000 years ago or so. So there were transient flank motion episodes that were identified, again, with INSAR, because we have some instruments, but it's very limited at that volcano as well. So INSAR helped identify a major transient flank motion episode that did not lead to a collapse in 2010. And then Schiffer et al. Did that. And then my group also looked at another flank episode that happened in 2014. Again, same question. All right, we have transient flank episodes, we have past catastrophic collapse, but are we also experiencing long-term persistent flank motion? And also, can we look at the triggers? So same questions. Then my former PhD student, Judith Gonzalez-Santana, looked again at hundreds of radar satellite images that were available from roughly 2007 up to present. She stopped in 2022. She needed to graduate, but we still have data there. And so she looked again at different satellites, ALOS-1, RadarSat-2, Cosmos SkyMed, Sentinel-1. And you have the time here on the x-axis. And basically on the y-axis, you have every dot here is an image, okay? And what we are going to do is we're going to process image pairs into an INSAR time series analysis. And to get high quality data, you need small perpendicular baselines and small temporal baselines and have a densely connected network. You had this 2010 eruption and transient slip episode. You had this 2014 eruption phase and transient slip episode that are included in this study. Just going to show you an example of one of these time series. This is Pacaya volcano here. Pixels that are of enough quality are shown as colored, and then the noisy ones are excluded and shown in white here. This is the summit of the cone, and the time series of the deformation is plotted for that area here on the unstable flank on this left plot. So you have time and cumulative displacements over time. And the reference for the zero displacements is here. All right, so it's basically going, over time, first image being the reference zero deformation. And you can see, you start seeing a pattern of ground deformation here in the upper edifice that is like accentuating with time, with a little bump here around 2014. And so basically this is showing you that the flank is also moving southwest, okay? For that type, 5 years or so time period. So we do see some continuous flank motion and some different rates or small upticks prior to 2014 eruption, and then the faster rate of subsidence flank motion right after the 2014 eruption. And then if we put everything together, so all the SAR time series together from 2007 up to 2022, we can see that it is a very interesting behavior that is happening at a volcano. Again, this is the time series of the deformation for that area here close to the unstable flank. And you can see that you have sometimes about 10 centimeters per year of flank motion. Sometimes it's less than that. It's like about 2 centimeters per year. And it looks like there is a correlation of accelerated flank motion with eruption phases. Like in 2010, the flank moved a lot after that for a while, and then it kind of slowed down a little bit. Same thing in 2014. There is an acceleration in slip until it kind of stabilized over time after that. So is Pacaya also experiencing persistent flank motion? Yes, this one is also doing it. then we can look at the patterns and we can model that. And so to look at potential mechanism and potential triggers. So basically, we looked at this time series and the ground deformation map for that period here before the 2014 eruption. And so my student and I, we basically modeled this ground deformation using a detachment, pretty shallow, normal detachment fault, slipping, dipping southwest, corresponding to that instability plane. And after 2014, that detachment fault was still active, but we also needed a dike intrusion, so magmatic dike intrusions that fed the 2014 eruptions and kind of accelerated and changed a little bit the deformation pattern. So then what we could do is we can look at the effect of the magma intrusion on the detachment plane, now that we have their geometry, by looking at Coulomb stress changes. So we are going to assume a source of stress, and then we are going to project the stress. Like, you guys know about this, but just so everyone is on the same page, you're going to project that source of stress tensors into a normal stress and a shear stress along a fault plane, which is receiving the stress. Okay, so that's the receivers. Basically, if your Coulomb stress changes are positive, in this case, it's like warm colors here, it means that your two receiver faults, were in positive Coulomb stress change areas, so the earthquakes might have been triggered by the source of stress. That was an example that I did at Kilauea volcano, looking at inflation of a reservoir triggering earthquakes in the caldera bounding fault system. So we can do the same thing here, and we can assume that the dike is our source of stress, okay, or dike opening. And then if we look at the Coulomb stress change map view and cross-section here, the detachment fault that we modeled is very nicely located in positive Coulomb stress change areas. And so we think that the opening of dikes at Pacaya volcano favor slip on the detachment fault. So we think that at that volcano, we have evidence for the flank slip being modulated by magmatism. So during really intense magma supply episodes where we have magma coming from depths and opening new pathways, new dike intrusions, we help this flank move faster. So we have accelerated slip during and after big eruption phase at that volcano. While when we don't have major dike intrusions happening, the system is more like an open system. We're not stressing really the system a lot. And so we have lower rate of flank motion during these periods of lower activity, basically. All right, so now last example, Kilauea volcano in Hawaii. Different case, because we are here dealing with a volcano that has a dense instrumentation on the ground. So this is a map view of Kilauea caldera is here. It was pre-2018 collapse. So we're on the Big Island of Hawaii, and we have two rift zones originating from the summit, along which we can have a lot of magma intrusions happening. We have 1 kilometer depth, small reservoir below the caldera, and about 3 kilometer depth reservoir under the south caldera, connected to the east rift zone. And we had a lot of activity happening at that volcano, basically a 30 years old eruption from 1983 up to 2018. Many lava flows originating from Pu'u vent here and going south. And the 2018 eruption happened here, very far away in the lower East Rift Zone area, and destroyed like many houses there in that area. So on top of the activity and the volcanic activity, this southern flank, delimited by the rift zone, basically is unstable and slipping seaward. And it can experience quite significant large earthquakes. Like in 2018, there was a 6.9 that happened along the flank interface. And in 1975, there was even a stronger one, 7.5 earthquakes. So very interesting interactions happening there between the landslide and the magmatism and the volcanic activity. We have a pretty good idea of where that de-Coleman fault plane is thanks to seismicity. So if we look at this figure on the right here, this is the map view of the south flank and all the relocated earthquakes from volcanic tectonic earthquakes that happened. And if you look at a east-west cross-section, and that's a north-south cross-section, the east-west cross-section really show you nicely that we have a pretty clear plane experiencing seismic activity. That is this de-Coleman plane along which the volcano is unstable. In terms of deformation pattern, so for most of these 20 years plus of that East Rift Zone eruption that I mentioned, most of the time the deformation it's an INSAR time series map again, map view. Most of the time it's subsidence at the summit and along both Rift Zone, and you can also see some deformation related to that slow flank motion, the persistent flank motion at Kilauea volcano. Looking at, compiling the motion along the flank motion, Wright and Clay in 2014 came up with this very neat compilation of the rate of slip on the unstable flank of volcano. And it is quite stable. So this is time, and this is distance in meters. So basically showing you 8 centimeters per year, 5 centimeters per year. So you don't have many, you have a few steps that are like related to magma intrusions along the rift zones, but it is quite steady in terms of flank motion. By the way, some of the steps, this is a GPS station here on the unstable flank. And if we look at the north-south component of the deformation over time, these little steps are the slow slip events that I mentioned before that were happening at Kilauea volcano. So you can clearly see them on the GPS stations that are on the southern flank. So what is our understanding of what's going on there? Our understanding is that, so again, this is Kilauea volcano, Big Island. If we take a cross section here, this is the topography and bathymetry that you have at that volcano. And so basically we have a summit area that is very active. We have magma supply beneath the summit and the rift zone. So we have basically a dike-like conduit that is from the surface up to about 8-10 kilometers depth. And this is the depth at which we see the de-Coleman plane interface, okay? The de-Coleman plane is about at 9-10 kilometer depth. And it is experiencing a seismic creep close to the magma intrusion zone, slow slip events, and it is experiencing also big earthquakes a little bit further offshore. Okay, so we think that there are different behaviors along that same fault interface happening due to different conditions. So basically, there is some sort of debate as well about the deep rift zone. So Poland et al., they said that basically creep, so the background deformation, that southern flank motion is due to loading, so gravity. And geochemistry petrology showed that there is no magma storage below 5 kilometers depth. However, most of the geodetic models from old leveling data, GPS, GNSS, and INSAR data include opening deeper than 5 kilometers. They include deep rift opening that induce slip on the de-Coleman. So we have some sort of contradiction here between the fact that there should not be magma below 5 kilometers, but we kind of need that opening to promote the slip on the de-Coleman. It is worth noting that all of these studies, including some by my group, are assuming homogeneous Earth, okay, with a Young modulus of 50 gigapascal most of the time. And again, you have this massive dike intrusion reaching quite deep, 9 kilometers, promoting slip on part of the décollement feature. So I'm trying to look at this and see what is the exact contribution of magmatism on the décollement slip. And how deep do we really need magma to be to actually help that slip on the décollement? So most of these models consider homogeneous single Young modulus, but we know it's not the case. In reality, obviously, we have layers, we have heterogeneities. And so one way to tackle this is actually, since we have seismic tomography data at that volcano, because there were, pretty good seismic stations and information. And so since we have seismic tomographic data, and in particular VP information available for that part of the volcano, we can actually calculate a Young modulus with the seismic velocity for the volcano. And if we do that, we find values that are not only 50 gigapascal on average, but we actually find values that vary from about 2 gigapascal close to the surface, and then increase over depths up to 100 gigapascal at about 10 kilometer depths. Variation in depths, obviously, and also spatially. So what I've been trying to do, what I've been working on here, I've looked at this cross-section again, and I basically did a simple 2D finite element model that is obviously very extended, so you avoid edge effects. But if you zoom in on my model, I have opening along a dike as a boundary condition, if you would like to think about it this way. So that's the dike push. And then you have the décollement fault. And I'm looking at the effect of the dike as a source of stress on the detachment plane, the décollement plane. So again, we have this problem that before we're using homogeneous Earth, we needed very deep magma, reaching 9-10 kilometers. So this is the result of one of these models, assuming a 5 kilometer depth dike. Okay, so that's depth here. And this is my profile, okay, with the bathymetry and everything. And so I did like a 5 kilometers depth, which seems to be the maximum depth allowed by geochemistry and petrology to have magma stored. And I looked at Coulomb stress changes induced by such a dike on the décollement at Kilauea. And I also plotted the areas that are experiencing the big earthquakes, okay? So the locked areas here. And if you do that, I mean, you are kind of in the positive Coulomb stress changes area, but you are definitely not in the biggest positive Coulomb stress changes area here. The right plot is just showing you the opening. So that's the UX displacement, the opening of the dike, basically. So it is slightly positive, but it remains quite small. However, if you start playing around with this layering by having multiple Young moduli and not just a single one, I did this preliminary test here where I have just 2 layers. I have a weaker layer for the top of the volcanic edifice, which has about a 5.4 gigapascal modulus. And then my base is, stronger. It has a Young modulus of about 100 gigapascal using, again, the seismic velocities that I showed before. And if you do that, you actually notice it's still 5 kilometers depth dike, okay? Same dike, nothing changed there. If you do that, you really extend quite dramatically that area of positive Coulomb stress change. And you also make it going deeper. So it's just preliminary results, but I think that we need to explore these heterogeneities and look at the effect of them, because we might not need to have such a deep dike if we include heterogeneities to promote slip on the décollement. still work in progress. And of course, we still need the dike to reach some depths. Like if you just have a dike that reached like 3 kilometers depth, like this one, even though you're considering the 2 layers like I did before, you're not helping the décollement slip. So it's work in progress, but I think we need to include that to have a better idea of what's going on here and the different stress triggering mechanism. So future steps include more layers. So I just did 2 for the preliminary examples, but we have information over a pretty good range of depths. And so we can implement more layers. And we can also start looking at variation spatially as well. And also I want to explore, variations of properties on the décollement as well. So I could allow some slip on the fold interface and explore how we can have basically transitions between a aseismic creeping section, a slow slip section, and a fully locked portion of the décollement. All right. So yeah, I think with that, I'm going to reach the conclusions here. So basically, what did we learn during this talk? I hope that you got the takeout message that creep, long-term persistent flank instability is way more common than previously thought. So I just added my contribution here and added 2 extra dots on that figure where we have at least 2 other volcanoes that are experiencing flank instability, longer term, persistent flank instability. We also, so again, these 2 volcanoes, and then even at volcanoes where loading and gravity are supposed to be the main driver for flank motion, it looks like magmatism can still have a big, influence. And so I think that flank motion is modulated by magmatism at active volcanoes, and this effect is more important than previously thought. And obviously, subsurface properties, rock properties matter. So other perspectives, for that big project. So again, I would like to look if I can kind of tease out the change in slip behavior at Kilauea between creep, transient, and other volcanoes between creep, long-term, transient effect, and catastrophic collapse. And also, where do the slow slip event fit in that story? Interestingly, for instance, Kilauea had this massive lower East Rift Zone eruption in 2018, and there is no new slow slip event happening there since then. Before that, it was pretty regular, every other years or so, there was a slow slip event visible on the GPS data and seismic data. And since 2018, nothing new is happening. So there must have been a big change in 2018 that affected the décollement. So I think rock mechanics can provide constraint, and some experiments that we're doing with Chris and his students might help as well, understanding some of these processes. And so I think that the key is to include rock mechanics, include different rock properties in numerical models, as long as we have enough constraint from subsurface imaging, obviously. And another thing that I'm working on that I'm very interested in is, we're looking at these slow, persistent, long-term flank motion. So we're looking at pretty small signals sometimes. We need, years of data to be able to identify them. And we are dealing with sources of noise in our INSAR data. And so we kind of need to tease them out from, signals from the noise. And so machine, and in particular deep learning approaches, can help us to denoise data and be able to extract smaller deformation signals. And yeah, that's it. Thank you so much.
Thank you, Christelle. That was fabulous. I'll invite people to unmute themselves and join me in thanking Christelle. Yeah, really a lot of interesting things. And yeah, okay, please use the reaction button at the bottom of your screen to raise your hand. It looks like this. And you can join me in, yeah, okay. This is what it looks like. I'm going to lower my hand because I'll wait to ask a question later. But yeah, Andrew Delory, please go ahead.
Hi, my question is the edifice of Mauna Loa big enough and close enough to affect the stress field in Kilauea?
Oh yeah, so there has been a lot of hypotheses there that basically Mauna Loa is this, like you said, massive edifice, and so it's buttressing basically the smaller Kilauea edifice, and Kilauea basically grew on Mauna Loa, southern side. So yeah, there is definitely a buttressing effect there that I did not take into account so far in my calculations that I showed here. But we are actually running some tests looking at the effect of buttressings by, pinning like a side of the volcano or something in our finite elements to see how it would help or not the instability.
Yeah, I guess I'm just wondering if it does more than just buttress it, if it actually applies some kind of a stress on the décollement on Kilauea.
Oh, yeah. It could. I mean, this is the same plane. I mean, the understanding is that the Coleman plane, you have big island and the flexure is what, because of the weight of Mauna Loa and the other volcanoes is what caused that décollement. So the plane keeps going under Mauna Loa. So yes, there should be a relationship. Some people have suggested stress change transfer between the two. Some people have suggested that when Mauna Loa is experiencing a lot of magma supply, Kilauea kind of shuts down for a little bit and doesn't have many eruption and vice versa. So yeah, I think it's super important. It's something that people have tried to touch on a little bit, but it's not very understood at this point.
Okay, thank you.
And before we go to Mark, I want to encourage everyone to participate in the discussions, particularly early career people. This is an excellent opportunity to join into a discussion. Mark, go ahead, please.
I was wondering, how would you separate this deep-seated slips that you've been talking about here from more like shallow slip events like landslides?
Okay.
How would you expect one to maybe
Right.
come along with?
So you're talking about the Kilauea case, right? With the deep-seated décollement, and you are wondering if we would be able to separate this slip at depth from shallower slips, right? Events. Making sure I understand.
But also
okay.
on a smaller scale, like maybe tens of meters thick.
Oh, well, I'm not looking at that type of scale. But to answer your questions about the décollement, the deep décollement versus shallow faulting, let me actually put up a figure here that could potentially help. So that's the cross section again, Kilauea, deep-seated décollement slip. There are faults visible at the surface on the southern flank. It's called the Hilina-Pali fault system. So you have scars and you have evidence for past slip on these faults. And we don't really know how they are connected, if that fault system is connected at all at the décollement at depth. But recently, we have not seen offset along the shallow surface faults at the volcano. It's interesting that they are not accommodating some of this. It's puzzling that they are not accommodating some of the deformation, to be honest. But yeah, we don't really know, and I don't think you can really see deformation signals along, again, these superficial faults recently using GPS or INSAR data. But it is indeed puzzling. And this is surprising that they are not accommodating some of this.
Yeah.
Mm-hmm.
Hey, thank you.
Yeah, please, go ahead.
Yes, thank you for this very interesting talk. I have a question on the numerical model of Kilauea that you created with Abacus, right? the
So
software?
say that again.
Did you
I use
create it in
Abacus.
Abacus?
Yes.
Abacus, yes.
Yes.
Because you
Yep.
said it's a boundary condition. Because basically, I'm also creating a numerical model of Kilauea, like at the moment, like it's in progress in Abacus.
Nice.
And I need,
nice.
And I want to implement the pressure as well of the dike in it. And
yeah.
I was wondering
So what
how
I did,
you did it.
Yeah. So as you know, you could go two ways, right? You could do the opening for a dike, similar to what the Okada solution would give you, basically. I went with the pressurized crack solution. So I did a overpressurized solution for my dike. That's what I used. So I did uniform overpressure, but not uniform opening. And it's just a pressurized crack, basically.
Okay. Thank you.
If that makes sense.
Yeah.
Feel free to email me. That's interesting.
Yeah, I will when I'm further looking into this. I'll definitely come back to you. Thank you very much.
Yeah, because my student did it the other way too. So we looked at the uniform opening, just the opening and not the overpressurized, overpressure. So I don't know. I feel like physically overpressure has more sense. It has more meaning, but yeah, you feel free to email me later. Definitely.
Yeah, I definitely will come back to that. Thank you.
Cool. Yeah.
Hi, Christelle, it's me. Fabulous talk, really clear and really interesting stuff. I've got a couple of questions. And the first one relates to the first example of Krakatoa. You were talking about, I think, about a meter, 10 centimeters a year for 10 years or so. And does that does that manifest reduction in the summit height too? Or can you get all this kind of creep landslide motion and still keep the summit at the same height?
Right. But well, that's a good question. So it's more like 10 centimeters per year. So it's not a meter, but over 10 years. Right? Yeah. Right. Yeah, so definitely that would reduce, that would make the entire thing kind of slip southwest. At the same time, you have volcanic activity, so you still have accumulation of materials.
I see.
So that's actually why we don't have information, by the way, at the very summit. It's because of all of that stuff that is being erupted, and that's why we don't have pixels, at the summit itself.
Yeah, you can't tell what's going on there.
So I guess looking at DEMs, that could be, I know that some people, so a colleague that from GFZ, Thomas Wauthier, has been acquiring some high resolution topographic data, DEMs, and he has one after 2018. So that would be a good way to look at that, I think, looking at the, DEMs acquired at high resolution to see exactly where the summit, topography and everything is. But yeah, you're right.
Yeah, so and then another part of it is, maybe even related to the last question. So if I think of it as, dikes and placing, maybe there's plenty of stress to make the whole thing move. But in that case, or if I want it to be, the whole thing to be almost like at the angle of repose, so it's just sliding, what do I have to assume about the coefficient of friction? It must be pretty low at the effective coefficient of friction that you get in a model like that.
Yeah, I mean, I did not really look into that, but I think we should look into that variation of friction coefficient. And especially, I would think, but again, we should talk about this, but I would think that shallower detachment faults, like the one at Pacaya and probably at Krakatoa, compared to deep-seated décollement, I think that would even matter more if it's shallow, right? Because then even effects from like rainfall and stuff would affect that, right?
Yeah.
But I've not looked into it for my Coulomb stress changes. I just assume a standard, friction coefficient. I didn't play around with varying that.
I see. I see. Okay, I have one more question, but I'm going to come back to it after Christian, please.
Yeah. Hi, Christelle. Thanks for your nice talk. I would like to know, because I'm more from the geodetic side, so I would like to know up to what extent the gap of you mentioned of the observation on the level of ground, but GNSS can be increased the inside of the transient signal in this flank instability over time, because in the picture that you put in fact there is a lot of gap in between. So this lack of the information, up to what extent can be improved our insight in this area?
Right.
This is
kind of... So it would be, no, you're totally right. So having GNSS stations, permanent GPS stations on the suspected flanks that are unstable would be super important. So like at Pacaya, Greg Wade from Michigan Tech has been working on trying to get a permanent GPS networks around the summit of the volcano. And yeah, it's continuous data. So you would have even a better idea, like you said, of the behavior of the flank. But unfortunately, we don't have that for many volcanoes. And so the way around it is to use very densely sampled SAR data, like Cosmos SkyMet. Cosmos SkyMet, you have like 4 satellites, so you can get an image every few days. It's not as ideal as GNSS permanent, measurements, but it's getting close to that. So yeah, definitely Cosmos SkyMet is the one that I would recommend to have the you can see that, right? You have way more data over time compared to, let's say, ALOS. You only had like one every few months or so. But yeah, definitely having GNSS stations would still be super valuable. Of course, INSAR would give you information about the spatial pattern of deformation on top of the temporal one.
Yeah, of course. But at the same time, at what extent, what is the precision or accuracy that is required for understanding this kind of phenomenon? Because I guess these transient signals are different than in the earthquake and then volcano. I don't know if you can give me a number of what is the range of the precision that you should be for.
Yeah. So, well, just to look at the Pacaya example, maybe, where we have different rates. So obviously something 10 centimeters per year, you would see that, obviously. If we are dealing with a few centimeters per year, if you have enough time, enough data over a long enough time interval, this is totally attainable with INSAR time series, as you can see here. But you need a long time series. You need many years of data. So I would say something above a centimeter per year, you should be able to detect it. Going lower might be possible depending on the conditions and the noise. Like you see on the Sentinel one here, we have a lot of noise, right? We have a lot of oscillations. It's actually not really noise. It's atmospheric effects combined with loading and unloading. So it's not really noise in the sense like it's not instrumental noise, but it's a signal that we don't want to look at if we want to look at this earthquake or volcanic eruption or landslide, right? But that complicates a lot. Like if you look at the scatter of that, I'm showing you with my hands, but I don't. If you look at, like the oscillations here, you have a scatter that is, like a few centimeters, right? So again, to detect slow motion, you would really need a long, like multi-year time period. And ideally, I mean, what we're trying to do, we're trying to kind of isolate these oscillations and remove them to only be left with like the longer term signals. So things like machine learning or independent component analysis, things like that can help.
Yeah, it's something we are trying to do the same for the earthquake, but using GNSS instead of INSAR. That is my question. I would like to know is our research can be, so to say, in the next step to be uploaded or to be applied in volcanic monitoring. by GNSS, because we are trying to face it with the low cost GNSS instead of geodetic in order to try to be more dense instead of to overcome this lack of the spatial resolution that can be, of course, from GNSS. Okay. Okay. Thank you.
Yeah. So I would say best bet Cosmos SkyMed and long, multi years. Yeah.
Okay.
Time series.
Okay. Okay. Thank you.
Mark, go ahead.
Another question. At Anakra Plateau, you see this like tenfold increase in the displacement rates in the 10 years leading up to it. And it's so far really the only example we have of satellite observations towards that catastrophic failure. Do you expect that the case of Anakra Plateau is like representative of the progress towards this failure, and you see that acceleration?
I'm not sure I can answer that at this point, because we're still looking into the volcanic activity and the intrusions. There is not a huge step, there is not a huge, there is a little increase in rate, but it's not like super dramatic right before the eruption that happened here, right? The 2018 collapse and stuff. So it's hard to tell if Anakra Plateau is representative of other pre-collapse. Like you said, we don't have many examples, right? And unfortunately, we don't have the GPS data, which would help us maybe looking at very short-term precursors before the collapse itself. So yeah, I don't know if it's a typical example and if it will be representative of the others. Not sure.
Thank you.
Christelle, it's Chris again. I have another question, and I also want to offer up, encourage anyone who's still here, people who are still here, to raise their hand and join the discussion, ask a question. But seeing no hands right now, I'm going to ask him. So, especially with respect to precursors, but I was already also thinking to myself, like, if we think of the nucleation size, you talk about something that's very similar to earthquakes, nucleating. How do you transition from slow and kind of plate tectonic motion versus to rapid dynamic motion? What do we think in these cases here? Do we have any sense about what the nucleation zone size might be for these cases?
I'm not aware of studies that looked at that, but maybe some people did, and in the rock mechanics laboratory, community, but maybe someone else know more about this.
Yeah, well, certainly there's models for it. And, in fact, it's another good reason to do the kind of experiments that I know you're talking about doing. You've already done some. In the context of rate and state friction, if you know some parameters, you can estimate something about it. Yes. The other thing that's useful to ask or think about is, the precursors. You say, okay, hard to see precursors in these data, but maybe there's something else. Maybe there's elastic wave speed changes. Maybe there's something in that data that could be recovered from nonlinear elastic effects or from passive noise.
And actually, talking about precursor, I did not quite mention this, but in the Pacaya example, because it's very hard to tell, but sorry about scrolling everything, but okay, if we look at the insert time series here for Pacaya, so the episode, eruption happened here, and right before it's going up, and the 2014 eruption and flank motion happened here, and you can see whatever you want to see, but it's also looking like it's going up right before. But these are so small signals that, again, it would require to kind of isolate them with PCA, ICA, or and we haven't talked about that in our papers because we only have 2 examples. Maybe if we have another eruption, we can maybe if we see that again, you know, but yeah, it's tricky for, you know, again, with INSAR, we are limited to the image acquisitions every few days at best, once a month, most of the time in the past. So that's where the GNSS stuff would be probably, or even tilt meters, you know, that could be pretty interesting to look at for very short time scale precursors. You know, or like what Esteban did with the seismicity, you know, at Erasu volcano, he had some very short-term precursors looking at the seismic data. That was super interesting.
Yeah.
But he needed his seismic station to be super close to the plane of landslide too.
Cool. Please, John, go ahead.
Yeah, sorry. This kind of gap that you mentioned, Christelle, can be so to say fulfilled by campaign mode, or you need to, or it's better to run this in a long-term processing. If you have some precursor or some information where should be procedure, this campaign mode can be useful, or definitely it's better than having a permanent station.
Yeah, it would definitely be better to have a permanent station.
Okay.
I mean, if you can have one permanent station and do campaign for the rest, you know, that would be great. But having at least one GNSS station where you suspect the flank is moving or something else is going on a slow motion process, that would, I think I'm not a GNSS expert, but I would think it would be better.
Okay.
Other questions?
Nothing in the chat, Chris, because I see stuff in the chat, but I don't.
There's been a few people. The only thing that's in the chat are thank yous and goodbyes.
Okay, cool.
Just
to make sure.
Yeah. Well, maybe you've answered everything. Sometimes it's useful to say goodbye slowly, but
oh yeah, and then if someone wants to ask me something, email me, shoot me an email, or I'm happy to discuss about anything, finite element models, or you know, other volcanoes affected by flank instability. I think it's really cool that it's still so unknown, and it's just a matter of looking at it carefully. And I'm sure there are many other volcanoes that experience that. So there are a lot of cool projects that can be done, I think.
Yeah, it's kind of nice. One of the things that can happen, of course, is the interactions, the questions, and the discussion that lives on much beyond what's happening right now. Well, okay. Maybe if there are no more questions, I'll just invite people to unmute, turn on your camera if you'd like to join me in thanking Christelle. Thank you very much, Christelle. Fabulous talk.